And in the first talk, David Roberson from the Technical University of Denmark is going to tell us about results and open problems in quantum isomorphisms. Please.
All right. Thank you very much for the introduction, and thanks for the invitation to talk. I think my talk is maybe not really falling into any of the three main topics of the workshop, and it's right in the middle. So I guess I'm kind of a palate cleanser. So hopefully it leaves a good taste in your mouth. So I'll talk about quantum isomorphisms, but at the end I'll actually focus mainly on just a more combinatorial problem of counting homomorphisms to graphs. And what I like about quantum isomorphisms is that it connects some seemingly different areas, in particular quantum information and algebraic graph theory and quantum groups. I'm not really going to go into detail about quantum groups in the talk, but if you have questions about them afterwards, then please ask. Okay, so I think probably everyone here knows what a graph isomorphism is, but just to make sure that we're all using the same terminology or notation. I mean, an isomorphism is just a bijection between the vertex set that preserves adjacency and non-adjacency. And I'm, of course, using this tilde notation to denote that two vertices are adjacent. And whenever you can find such a map, we say that the graphs are isomorphic. And we write, use this congruent symbol here. Everyone can see the markings I'm making on the slides. Okay, good. This is my first time combining Beamer with this like iPad pencil thing, so hopefully it goes well. Now, of course, this isomorphism is just exactly sort of what you think of when you talk about two graphs sort of being the same. They're the same up to relabeling the vertices. And there's a very nice algebraic or matrix formulation, in particular in terms of the adjacency matrix. So probably everyone knows that the adjacency matrix of a graph G is just a 0-1 symmetric matrix that has a 1 in, say, the UV entry of U and V are adjacent in your graph. And then two graphs are going to be isomorphic if you can sort of permute the rows and columns of one of the adjacency matrices. So here, this matrix P is a permutation, and you want to permute the rows and columns the same in the same way to get the adjacent matrix of the other. This is all pretty obvious, but it motivates some upcoming stuff. So this is graph isomorphism, and what we want to do is come up with a quantum analog of this. And the way we're going to do that is we're going to first define a type of game that captures this notion of graph isomorphism. So we defined something called the GH isomorphism game for two graphs G and H. And the idea is that we want two players that are kind of working together to convince some referee that two graphs G and H are isomorphic. And the way the game works is that the referee is going to send each of the players, Alice and Bob, a vertex of the graph G. And they're each going to respond with a vertex of the graph H. And in this case, I'm going to make things a little simpler and just assume that the graphs G and H have the same number of vertices. So this gets rid of the sort of necessity of being able to sum them vertices from either graph. And in order to win the game, what we want is that the vertices that they receive from the referee that were vertices of G, that they're related in the same way as the vertices that they responded with. So that means that if this G and G prime were adjacent, then H and H prime should be adjacent. If they were equal, they should be equal. If they G and G prime were distinct non-adjacent, then H and H prime should be distinct non-adjacent. And the kicker, I guess, is that they're not allowed to communicate during the game. So they can get together beforehand and agree on a strategy, and they know both of the graphs ahead of time. But once they receive their questions from the referee, they can't talk to each other. So Alice is not going to know what G prime is, and Bob's not going to know what G is. you can think that they're only playing sort of one round of this game. So the referee is only sending them just the one vertex each. But you want them to have some strategy that wins with certainty. So they never lose, no matter what questions I get from the referee. And it's not that hard to see that actually you can win this game perfectly if and only if actually the graphs are isomorphic. So if the graphs are isomorphic, then you can just use some isomorphism, say F from G to H, and you respond according to that isomorphism. Alice gets her vertex little g, and then she can just respond with F of little g. And Bob does the same thing, and they'll always win. And then the converse is not so hard to show either. Essentially, if they're using a classical deterministic strategy, then each of them just has a function that takes their inputs, their outputs, and the conditions of the game require that these two functions are the same for Alice and Bob, and that they are in fact an isomorphism. Okay, so this is what we mean by this game capturing the notion of isomorphism. And so now we're going to use it to define a quantum analog by considering the same game. So the game won't change. All the sort of the inputs and outputs of the game are classical. The only thing that's going to change is that we're now going to allow Alice and Bob to have access to some quantum strategies. Okay, so what's a quantum strategy? So first of all, Alice and Bob are going to share some quantum state. And then whenever Alice gets her vertex little g, she's going to perform some quantum measurement on her part of the state. And this measurement is going to depend on the vertex she received. And she's going to get some outcome, little h, from the graph h. And then Bob's going to do the same thing, but with his own set of measurements. And also he's going to respond with some h prime. So more technically, this shared quantum state that they have, this is just some unit vector in a Hilbert space H. And I mean, in principle, this Hilbert space might be infinite dimensional, but sort of intuitively speaking, I mean, it doesn't really hurt to think of it as some finite dimensional complex space, C to the n. Okay, and then what's the measurement? Our measurement is just a collection of positive operators, I guess bounded linear operators, such that they sum up to the identity operator. And so Alice has these measurements for each vertex little g, and Bob has the same. And what we require is that every one of Alice's measurement operators commutes with every one of Bob's measurement operators. This doesn't mean that all of Alice's measurement operators have to commute with themselves. Okay, and if they play according to such a quantum strategy, then what happens is that they're not going to have some deterministic strategy necessarily. They're going to have some kind of probabilistic strategy. And the way you determine these probabilities, so here this probability P of H comma H prime given G comma G prime, this corresponds to the probability that Alice and Bob would respond with H and H prime, assuming that they guide vertices G and G prime, respectively. And so this probability is just equal to this inner product here. So here, we just multiply these two measurement operators and apply that to the state psi, and then take the inner product of psi. And because of the conditions on these measurement operators, this is going to give you some probability distribution. And then we use this to define quantum isomorphism. So we say that two graphs are quantum isomorphic, and we denote it using this congruent sub QC if there's some perfect quantum strategy for the game. By perfect, I mean it wins for probability 1. Another way of saying that is that these probabilities are 0 on any sort of losing set of inputs and outputs. And the reason that we're using this Q sub C instead of just Q is because sometimes this framework is known as the quantum commuting framework. There's a slightly different framework where instead of taking the product, you take a tensor product here. And in that case, you don't require this, but actually your Hilbert space has some tensor product structure. And sort of Alice's measurement only applies to one part of the tensor and Bob's to the other. But we're going to focus on this more general scenario. Okay, so this is the definition of quantum isomorphism. And as you can see, it kind of has a lot of parts involved. So there's this unit vector, and there's all these measurement operators for Alice and Bob. And so it would be nice if we can somehow simplify this a little bit. And in fact, we can do that. We can get a very nice matrix formulation, perfectly analogous to the matrix formulation for isomorphism. So we just need to define the right kind of matrix, in particular, something called a quantum permutation matrix. Or if you're working quantum groups, it's known as a magic unitary. So here, the entries of our matrix, curly P, they're not going to be just some numbers, they're actually going to be elements of a C-star algebra. Okay. If that's scary, then just pretend that they're matrices. It's not exactly the same thing. This is more kind of like an abstract way of defining an algebra of bounded linear operators in the Hilbert space. But intuitively speaking, you can just imagine that this is a matrix whose entries are matrices. Okay, and the requirement is that each entry is a projection. So it squares to itself and it's equal to its own conjugate transpose, or I mean, if you're in the abstract C-star algebra case, it's equal to its own star. The other condition is that if you sum along any row or column, then you're going to get the identity in your C-star algebra, or the identity matrix. And what's not so hard to see is that if your C-star algebra were just the complex numbers, then you actually just have a permutation matrix. Because if your entries are just complex numbers, then already from here you get that they have to be 0 or 1. And then this condition says that there has to be exactly 1, 1 in every row and every column. So we get exactly a permutation matrix in this case. And so we see this is some kind of, I guess you would say maybe operator or non-commutative analog of permutation matrices, which I think just looking at the definition seems like a very natural thing to consider. And when we first sort of stumbled upon this, we sort of wondered why we had maybe never heard of it before. But of course, we were not the ones to define it. The quantum groups people have been working with it for over a decade, I believe. Okay, and then the theorem is exactly what you would expect. It's that two graphs are quantum isomorphic if and only if you can find a quantum permutation matrix that satisfies this equation here. Okay, now this matrix just has integer entries, and this matrix has some funky algebra or matrix entries. But of course, I can multiply integers by matrices or by algebra elements, so I can still sort of naturally perform this matrix multiplication here. More formally, I require that these sums are equal for all little g and little h. Okay, so this gives us this nice matrix formulation. One thing that implies actually is that if two graphs are quantum isomorphic, then they have to be co-spectral, because this quantum permutation matrix actually will be a unitary matrix. It's not necessarily obvious from the definition, but that will be the case. Okay, and this theorem already kind of uses a little bit of quantum group theory, not a lot. You can get almost the exact same theorem using, I would say, like sort of standard results from quantum information from the theory of non-local games. But you would need that this quantum permutation matrix, the entries to live in a C-star algebra that have something called a tracial state. So you get a little bit extra requirement that you need. But then if you use quantum groups, you can throw away that condition. Okay. So then we have that nice, I guess, formulation, but it's still not obvious that this notion of quantum isomorphism is even different than isomorphism. I mean, are there even any pairs of graphs that are quantum isomorphic but not isomorphic? And this is sort of when we first started defining this notion. I mean, this was sort of the last thing we figured out before we started actually submitting papers places. So, I mean, we had figured out a lot of kind of like necessary or sufficient conditions, but we didn't actually know that, a lot of, I guess, necessary conditions. We didn't actually know there were any interesting examples possible. But it turns out you can get some nice examples, and that's what we'll look at. And the way you do it is you actually do some sort of reduction from some examples of some other things where you have kind of separation between some quantum and classical scenario. So we're going to look at binary linear systems, and this is nothing but a linear system over Z2. So we have some mx equals b, and these are matrices over, I guess, F2 or Z2, depending on how you like to think of it. And then what you want is that you need to come up with sort of a quantum analog of this thing having a solution. And the way you do it is that you essentially convert these linear relations, which are just sums of some variables, into a kind of a multiplicative form. The easiest way to see is just an example. So here we have this equation, x1 plus x2 plus x3 equals 0. And this gets converted to x1 times x2 times x3 is equal to identity. So this, I'm converting to a multiplicative form and then also generalizing to like sort of a matrix or operator valued solution. And then if the right-hand side were 1, it becomes -1 over here. Right, so you're just converting 0, 1 to 1, -1 variables. And the way you get sort of this quantum generalization is that instead of just allowing plus or -1 values assigned to these x sub i's, you allow some operators to be assigned to them. But you need that all these operators that they square to identity, and they're self-adjoint. The other thing you want is that if two of them appear in the same constraint together, so in this case, say x1, x2, and x3, they appear all together in this one constraint, then you want them to commute. In particular, this means it doesn't matter which way you multiply them, right? I could have had x2, x1, x3, and it wouldn't have made any difference. And then the last thing is just the sort of that they satisfy the system, so to speak, right? Sort of that they actually do satisfy these equations here. Okay, so that's what a quantum solution to this binary linear system is. And whenever we find one, we say that it's quantum satisfiable. Okay, and what we want to do is we want to construct a graph out of these binary linear systems in hopes that we can somehow use an example of a linear system with a quantum solution but no classical solution to get a pair of graphs that are quantum isomorphic but not isomorphic. And so how do we do that? Well, let's just consider this simple binary linear system with two equations. So we have x1 plus x2 plus x3 is 1, and x1 plus x4 plus x5 is equal to 0. And the way we define this graph, again, the best way is to just show you an example. Basically, for each one of these constraints, we're gonna make a vertex for every satisfying assignment just to the variables appearing in this constraint. So here I have just x1, x2, and x3, and I want to make a vertex for every satisfying assignment just for this one equation. So in particular, I would have to assign an odd number of ones to these variables. So I could have 1, 1, 1, 1, 0, 0, 0, 1, 0, or 0, 0, 1. And similarly, this equation, I have to assign an even number of ones. So I could have 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0. And then what I do for the edges is that I put an edge between two vertices if they're somehow inconsistent. So this means that they share some variable, and the thing they've assigned to that variable is different. So let's look at just these first two vertices on the top. So here I've assigned x1 1. That's the thing in the first coordinate. And here I've assigned x1 0. So these sort of partial solutions are inconsistent, so I put an edge between them. And that's how you construct this graph. So it's relatively straightforward. And then the theorem is really nice, right? So the theorem is that, well, this linear system will be classically satisfiable, so meaning there's just some solution, if and only if this graph corresponding to the linear system is isomorphic to the graph corresponding to the same system but the homogeneous version. So I put all zeros on the right hand side. And then the quantum analog is exactly the same thing. You just add the word quantum everywhere. So it has a quantum satisfying assignment if and only if the two graphs are quantum isomorphic. So now we just need to find binary linear system that's quantum satisfiable but not satisfiable, and then we'll get a pair of graphs that are quantum isomorphic but not isomorphic. Oh, and as a corollary, what you get is that quantum isomorphism is undecidable because it's known that determining if one of these linear systems has a quantum solution is undecidable. That's a really important result by William Slofstad. And just a remark, this is essentially, it's the only construction that we really know for getting these non-isomorphic with quantum isomorphic graphs. There's another construction by Musto, Reuter, and Verdon that's based on subgroups of central type of the automorphism groups of some graphs. But as far as I know, they were never actually able to construct any new examples of quantum isomorphic graphs, so ones that we didn't already know about using this. So it's basically the only construction. So one open question, I guess, since this is an open questions conference, right? How can we find some more examples? I mean, is there another construction that'll work and give us some interesting examples? Okay, so I've sort of claimed that there are such systems that have a quantum solution but no classical solution, but I haven't really explained why. So there's this really nice result by Arkhipov that actually constructs systems from graphs. And the way you do it is you just use the incidence matrix of a graph. So probably everyone knows what this is, but this is just a graph that's rows indexed by vertices, columns by edges, and then there's a 1 if sort of the vertex and edge are incident to each other. So that means the vertex is one of the endpoints of the edges. And so what you do is you use this incidence matrix as your coefficient matrix for your linear system. And then what you want to do is you want to pick a vector B that has odd weight, meaning an odd number of ones. Actually, it doesn't matter where you put the ones as long as there's an odd number. In fact, the graphs you get will be isomorphic if and only if the parity of this vector B is the same. And then what happens is that, well, mx equals b is never going to be satisfiable classically. And this basically boils down to the fact that a solution here would give you a subgraph of G that has exactly one vertex of odd degree, which of course everyone knows is impossible. But it turns out that it's quantum satisfiable if and only if G is not planar. And of course, there are plenty of examples of graphs that are not planar. So we can find some examples. So what's a not planar graph? It's K33, right? So here's a graph, and so this is for the non-homogeneous system here, and then the homogeneous one is here. So right, everyone can see that these are not isomorphic, right? This is clear. Okay, actually, Karen, I don't know if Karen's here, but if she is here, she should be excited because this is the derangement graph for S4, right? So she really loves this thing. And actually, this other one is also a Cayley graph for S4, but you take the derangement graph, which has connection set all the I would call them like double transpositions, like 1, 2 times 3, 4, and the 4 cycles as your connection set. But you replace the 4 cycles with just the transpositions, and then you get this graph. So it's also a nice Cayley graph. And these are quantum isomorphic, but they're not isomorphic. Okay, so that's sort of, I guess, like a pretty quick summary of some of the early results about quantum isomorphisms. And now I'm going to talk about something a little bit more recent, which relates this quantum isomorphisms to homomorphism counting. By the way, how much time do I have? Is it 45 or 50 minutes? 50. Okay, great. There is actually this really nice classical theorem of Lobos from about 50 years ago, and it characterizes isomorphism in terms of homomorphism counts. So I'm going to use this notation HOM with little h. of F comma G to just denote the number of homomorphisms from F to G. And a homomorphism, in this case, this is just a function from the vertices of F to the vertices of G that preserves adjacency. So things like colorings or something like this is a homomorphism. And what Loa showed is that two graphs are isomorphic if and only if they have the same number of homomorphisms from any graph. In one direction is obvious because if they're isomorphic, they obviously have the same number of homomorphisms. The other direction is not sort of incredibly hard, but it is sort of a very nice result. And what we were able to show with Laura Menchinska is that there's a quantum analog of this for a quantum isomorphism. Two graphs are quantum isomorphic if and only if they have the same number of homomorphisms from any planar graph. And I'm not going to go into the details about the proof. I would just say briefly that the proof sort of goes through quantum groups. But in fact, I mean, sort of the real meat, almost the whole proof is sort of a lot of arguments about proving planarity of things, or showing you can construct all planar graphs using certain constructions. So the proof really, in a certain sense, is very combinatorial, but it does use this nice kind of these sort of connections that are mediated by quantum proof theory. So I think it's nice that it kind of combines all these different areas. And the other thing, I guess, that's nice about it is that, okay, it's fairly surprising. I mean, I was surprised when we figured it out. So I mean, I think it's pretty interesting. Like I said, I'm not going to go into the details about the proof, but I do have some slides at the end that have details about the proof if anyone is interested. Okay, and then I mentioned before that quantum isomorphism is undecidable. So of course, this gives us this nice corollary that this sort of somehow like purely combinatorial problem is undecidable. So determining if there's some planar graph with a different number of homomorphisms to two given graphs, this is an undecidable problem. In fact, it's complete for the class RE, recursively enumerable problems. Okay. As opposed to checking for all graphs, which is, I guess, at worst, quasi-polynomial time, right? Because it's equivalent to isomorphism. Okay, so let's put this into a bit more context. So for any given family of graphs, curly F, I'm going to define this relation, congruent sub F, to just denote that two graphs are the same number of homomorphisms from any graph in curly F. And then there's some sort of nice results that say, okay, well, given a certain family, you get some nice relation out of this. So of course, we already talked about the Lovatz's result, which says that if you look at all graphs, you get isomorphism. Of course, if you look at just cycles, then you get co-spectrality. This is usually phrased in terms of like, okay, two graphs are co-spectral if they have the same number of closed walks of any length. If this is a closed walk of length k, it's just a homomorphism from a case. If you count cycles and paths, then you get co-spectral plus co-spectral complements. If you count homomorphisms from trees, then you get what's called fractional isomorphism. So this is like if we took this equation we had before, where we had this for isomorphism, where P was a permutation matrix, and we relax it to P just being a doubly stochastic matrix, then this is fractional isomorphism. And this is a really nice result proved first proved by Dvorak and then independently by Delgar-Rattan later. And they actually both proved the generalization that if you look at graphs with tree width at most k, then you get the relation you get is that the graphs are indistinguishable by what's called k-dimensional Weisfeld. And more recently, Grower showed that if you look at graphs of tree depth at most k, then you get some kind of nice like logic formulation. So it's indistinguishable by first order logic with counting of quantifier rank at most k. I don't really know what that means, but I mean, it's interesting that you can get such a sort of a tight characterization for this family of graphs. And I should point out that, I mean, also for this k-dimensional Weisfeld alignment, there are some many different formulations, including some in terms of this first order logic. So there's some connection there. And of course, our result is for planar graphs, you get quantum isomorphism. I should point out that it is known that there are some proper subfamilies of graphs that just give you isomorphism again. So if you, Dvorak also showed that if you look at two degenerate graphs, then you get isomorphism. So a graph is two degenerate if any subgraph of the graph has minimum degree at most 2. So this will also give you isomorphism. Okay, and then I think a nice question is, can you find some class that's sitting strictly between the class of planar graphs and the class of all graphs, such that this relation you get is tractable? Because if you can find such a thing, you maybe can use this to construct some new examples of quantum isomorphic but not isomorphic graphs. Because if the relation is tractable, then maybe it's easier to construct pairs that satisfy that relation but aren't isomorphic. And this relation would have to be stronger than quantum isomorphism. Okay, but maybe it's impossible. Okay, I think this is kind of a cute application. I don't think it's very practical, but it's some relation to this, to the, the 4-color theorem, which, I mean, if you can connect something to the 4-color theorem, you should probably mention it. All right, so let's look at these two graphs that we saw were quantum isomorphic before. I'm just going to call them G and H now. So this is G, this was the homogeneous one. Remember, this is the derangement graph for S4, and this is another Cayley graph for S4, but with a different connection set. So G, actually, it has chromatic number 4 and also clique number 4. And that means that any graph F has a homomorphism to K4, i.e. it has a 4-coloring, if and only if it has a homomorphism to our graph G. And that's true for any graph. Now, because G and H are quantum isomorphic, this means that for planar graphs F, you have a homomorphism to H, if and only if you have a homomorphism to G, right? I mean, actually have the same number. So if you have any for one, you have also some for the other, if and only if. And what this means is that if a planar graph F is going to be 4-colorable, if and only if it has a homomorphism to H. Okay, well, that's only interesting if somehow having a homomorphism to H doesn't already imply you have a homomorphism to K4, but actually it turns out that it doesn't imply you have a homomorphism to K4. In particular, this graph H has chromatic number 5, so it has no 4-coloring. So somehow for general graphs, it's sort of easier to have a homomorphism to H than it is to have a 4-coloring. So it seems like you get a reformulation of the 4-color theorem that is sort of somehow like a priori easier to prove, right? Now, in practice, it's probably actually harder to prove that some planar graph has a homomorphism to this weird 24-vertex graph, but it's still interesting. The other thing that's kind of, I guess, maybe a bit of a bummer is that you can actually prove this kind of classically. You don't really need to use this quantum isomorphism result. It turns out you can prove it just using like a Tate's reformulation of the 4-color theorem in terms of showing that any planar bridgeless cubic graph has a 3-edge coloring. And in fact, you will get a similar reformulation if instead of using, so here we use K33, remember, to build these two quantum isomorphic graphs. If you use any non-planar connected cubic graph that is 3-edge colorable, then you'll get a similar reformulation of the 4-color theorem, but you will also be able to prove this using Tate's reformulation. So somehow these cases are not interesting, but maybe there are some other cases that are interesting, some are like sort of truly novel. But I don't know. Okay, so now I'm going to talk less about, say, quantum isomorphism or quantum anything, and more just about counting homomorphisms in general. And this, I guess, is kind of newer stuff. It's not published anywhere, and I haven't actually really talked about it. So hopefully you find it interesting. I think it's pretty neat. So, now, what we're going to start with, what we're going to do basically is we want to construct some pairs of graphs that we can pretty well understand when some graph has a different number of homomorphism to those two graphs. So we'll start with the construction. and then we'll sort of get to the results about the construction. So here, just some notation. So that if I have some graph, I'll just use E of V to denote the edge's incidence to some vertex V of that graph. So now I take some graph G, and I take some subgraph of the vertices, and I'm going to define this graph G sub U. And the vertices of this graph are going to be some ordered pairs, where the first thing in the ordered pair is just some vertex of G, and then this second thing, S, in the ordered pair, this is going to be a subset of the edges incident to V in the graph G that has parity it has parity, it's odd parity if that vertex V was in that subset U, and it has even parity if it were not in that subset U. And then two of these ordered pairs are going to be adjacent if the first coordinates were adjacent in G, and also somehow these subsets sort of agree on the edge between U and V. So this says that either the edge UV was in both S and T, or it was in neither of S and T. And actually, this construction is essentially almost the complement of this construction we saw before using linear system games coming from the incidence matrix of your graph. The only difference is that there we were putting edges between these partial solutions that were inconsistent. Here we're putting edges between partial solutions that are consistent, assuming they actually do share some variable. Okay. So it's very close to just taking the complement. But this is sort of like a more kind of just graph theoretic description without sort of resorting to these linear systems. Okay, so this is this graph construction. And it turns out actually the subset U, there's basically just two choices, and it just depends on the parity of U. So if you have U and U prime that have the same parity, they'll be isomorphic. You'll get isomorphic graphs, and if they have different parity, then you'll get non-isomorphic graphs. So we just denote sort of the even parity ones by G sub 0 and the odd parity ones by G sub 1. We're not going to care so much about sort of the particular subset U that we're going to choose. We can, for the even parity, I guess it's natural to pick the empty set. Okay, but the point is there's essentially just two cases for this construction. Okay, so here's an example. So here's the graph G. It's just this K1, 3. And then here are the two graphs you get. I tried to draw them so that somehow the vertices kind of correspond to the vertices of the original graph G. So here in the middle, these are the four vertices that come from this vertex, right? Because you take the ordered pairs where we have this vertex and then an even subset or an odd subset, depending on what you choose, of the edges incident to that vertex. So there's 3 edges, so we have to pick an even subset. So it's going to be 4 possible vertices. Here I've cheated a bit. So the second, I don't know if it's big enough to see actually, but the second thing in the ordered pair is actually just, instead of the edges, it's the neighbors, the subset of neighbors, because it's easier to write. But I think maybe it might be too small. Anyways, so these are some simple graphs. This is just K1, 3, but I've just subdivided every edge. And this is just a 6 cycle, but also with an extra isolated vertex. Maybe you guys know that these graphs are co-spectral, and they have co-spectral complements. In other words, they have the same number of homomorphisms from any cycle or path. Okay, cycles and paths are essentially the graphs that don't have any vertices of degree 3. So that's maybe something interesting to note. Okay, another I guess more interesting example is if you take the graph K4, then the 2 graphs you get are actually 2 strongly irregular graphs with parameters 16, 6, 2, 2. What's known as the 4x4 rook graph, and then the Shirpanda graph. So I guess these are kind of some famous graphs, so it's kind of interesting you can construct them in this way. This is a very sparse slide, but I'm going to make up for it on the next slide, so don't worry. Okay, so now we want to think about counting homomorphisms to these 2 graphs. Okay, so one thing to note is that both of these graphs have a homomorphism back to the graph G, because we can just sort of project onto the first coordinate. Because remember, part of the definition of these graphs, the edges in these graphs, was that the first coordinates need to be adjacent in G. So this projection is in fact a homomorphism. And so based on this, we're going to be able to partition the set of all homomorphisms from F to one of these graphs in the following way. So we denote the set of all homomorphisms from a graph F to a graph G by this capital H hom. So if I had lowercase, it's the number, and now it's the whole set. And now we're going to sort of partition the homomorphisms from F to GI according to somehow the homomorphism you get that goes from F to G when you compose with rho sub I. So suppose I have some homomorphism var phi that goes from F to GI. I can compose this with rho I, which is a homomorphism from GI to G, and that will give me some homomorphism from F to G. And so depending on what this homomorphism is, I'm going to sort of partition all of these homomorphisms here. So, right. So anytime I had a homomorphism here, I can get a homomorphism to G, and conversely, if I have a homomorphism from F to G, I can look at this sort of particular subset of homomorphisms from F to GI. Okay. Right. And what's really interesting is that once you sort of partition according to the sort of this, I guess, according to this rule, it's easy to sort of count the homomorphisms. For a fixed homomorphism psi, actually these homomorphisms are in bijection with the solutions to some linear system. Now, I don't want to go into detail about what this matrix M psi is or what this B sub I psi is. The only thing that really matters is that for I equals 0, this vector is the 0 vector. And for I equal 1, the vector is not the 0 vector. Okay. And essentially, the reason this works is because once I fix this homomorphism psi, this is sort of telling me, okay, for any vertex in F, I know kind of the first coordinate of the vertex I'm mapping it to in G sub I. And then I can just encode the choice of the second coordinate, which is this subset, in terms of some linear system, with basically some indicator variables, and they have to satisfy some linear requirements. And what you get out of this is that, okay, you get this corollary, which has sort of 3 parts. First of all, for any psi that's a homomorphism from F to G, you get that sort of this part, this of all of the homomorphisms from F to G0 is not empty. And this is just because you always have the homogeneous solution. For when I equals 0, this is just the 0 vector here, and so x equals 0 is a solution. So you always have some solution. Okay. The next thing is that, what about for I equal 1? So in this case, well, either I have no solution, right? In this case, it will be a non-homogeneous system. So I might have no solution. So I have 0 homomorphisms in this set. Or if there is at least one solution, then actually it's just somehow like a coset of the solutions for the homogeneous case, right? So it has the same size, right? So the only possibility is that you have no homomorphisms or the same number as for G0. And what this means is that I will always have at least as many homomorphisms from F to G0 as from F to G1. And I will get strict inequality if and only if I can find some homomorphism from F to G such that the number of homomorphisms here is 0. So basically this corresponds to one of these equations for some psi, and for I equal 1 not having a solution. Okay. So, I meant to point out actually, as a special case, if you plug in f equal to g and psi equal to the identity map, then you get that this is in fact 0, and that tells you that the number of homomorphisms from G to G0 is bigger than the number of homomorphisms from G to G1, and this is in fact how you show that they're not isomorphic. Okay, so now I'm going to introduce this kind of linear algebra lemma. And I just found this name on Wikipedia this morning. I thought it was really funny because it sounds like some sort of like Jason Bourne movie title. It's for some reason called the Fredholm alternative. But it's basically just Farkash's lemma. But I guess Wikipedia claims that it's not really that because it's only dealing with equalities. Okay, it says that some linear system, and this is over Z2 for us, but I guess it's over any field. It doesn't have a solution if and only if this system does have a solution. And what this is going to allow us to do is that it's going to allow us to take sort of this condition of some system has no solution, which somehow is very hard to get a certificate for, I guess, to this system, this other system does have a solution, which then you have a natural certificate for. And so we just apply this to sort of the previous corollary, and it says that the number of homomorphisms from F to G0 and from F to G1 is different if and only if there's some homomorphism from F to G such that this equation has a solution. And now what we can do is we can interpret such a solution combinatorially, and we get some combinatorial condition. But to explain that, I'll have to introduce terminology, and I'll try to be relatively quick since I'm running out of time. So this is a definition. I just put it in 3 parts because when I put it in a big paragraph, it looked like it was impossible to read. So take G to be some connected graph, H is any graph, and then psi is some homomorphism from H to G. Then we're going to say that a vertex of H is odd or even if this holds. So what this says is that the number of neighbors of A in the pre-image of a vertex of G such that this vertex of G is adjacent to the image of A is either odd or even, in every possible case. So maybe it's better to just show you a picture. So when I say that, so here the graph is G. So here, this vertex is even because somehow in this fiber over here, it has an even number of neighbors. And in this fiber over here, it also has an even number of neighbors. And that's what this first condition is saying. Somehow in every possible fiber where it could have neighbors, it has an even number. And so if I started with this 5 cycle, then a vertex here, which is, these are the pre-images of this vertex. So these can only have neighbors over here and over here. And this one has an even number in both of those. Whereas this one has an odd number over here and also an odd number over here. So we say that this is an odd vertex. So if you have, if you graph H and this homomorphism psi has the property that every vertex of H is either an odd or an even vertex, and also there's an odd number of odd vertices in all of these pre-images. So in this case, there's one odd vertex. Then we call it an odd couple for G. So here's just one specific example. And then what you get is that you can now sort of interpret this solution Y that we saw in the previous slide combinatorially, and you get the following there. It says that if you have a connected graph G, then you have a different number of homomorphisms from F to G0 as from F to G1, if and only if you have some homomorphism from F to G and some subgraph H of F such that this is an odd couple for G. And what that would mean is that, so if I go back to this picture, your graph, so here somehow this is kind of our subgraph H. Your graph F, it might have some extra edges between here or between here, and it might have some extra vertices in some of these fibers, but it shouldn't have any edges between fibers that somehow aren't adjacent in G. Okay, but one thing that's sort of easy to see is that if you have an odd couple for some graph G, then this graph H, it has to have maximum degree, at least the maximum degree of G. And this is just because if I look at a vertex, if I take a vertex in G that has maximum degree, and I look at its pre-image in H, then it has to contain an odd vertex, and this odd vertex has to have at least one neighbor in all of the sort of neighboring fibers. Okay, and so from this you can get that if I take F to be the family of graphs with maximum degree D, then actually these two graphs, G0 and G1, will be sort of F related, where G is this K1 D plus 1. And this is, I think, interesting because it shows that if the number of homomorphisms, counting the number of homomorphisms from graphs of degree at most D doesn't determine a graph of the isomorphism. And I kind of would have guessed that it does. I would have thought that, oh, if I know the number of homomorphisms from all graphs with degree even at most 3, then it should determine the graph of the isomorphism. I mean, there's a lot of complexity in graphs of degree at most 3. But it turns out that that's not the case. So here's an example. So this is for G with K14. These are the two graphs you get. So these two graphs have the same number of homomorphisms from any graph of degree at most 3. And you can see it doesn't even determine like whether or not you have an isolated vertex. This has an isolated vertex and this one doesn't. So I don't know, I think it's pretty surprising. So, okay, I'll just go ahead and put all these on the screen and I'll say I'm done. Yeah, okay. So I guess the one question I want to highlight the most, I'll just say that, is that can you somehow show that if H psi is an odd couple for G, then H must contain G as a minor? So I think this would be really interesting, because if it's true, then you can show that somehow these relations are always distinct as long as you're looking at two different classes that are closed under both minors and disjoint unions. Okay, and then I'll end there.
Thank you very much for the talk. Very interesting as always. But before we proceed to the questions, and you're still here, I would like to make an announcement. So I'm sure you like the talk and maybe you would be interested in learning more about this topic. Then you should definitely know the following. So they're going to be lectures about quantum morphisms and isomorphisms of algebras starting May 13th. This is going to happen every Tuesday, Thursday over the summer term. So please, you're welcome to come. Then if you want to know how to come, then you should at least check our conference website. There will be more information there about it. So David Roberson is going to be the speaker for the quantum morphisms, and Crystal Guo, who know probably from the Algebraic Graph Theory seminar, she's working in this area. She's going to be talking about isomorphisms and algebras. So you should definitely check it out. It's very interesting. I'm going to be there. Yeah. Okay. Okay. Thank you for the talk again, and let's proceed to the questions now. So, anybody has questions?
So, David, you can get pairs of graphs that are quantum isomorphic but not isomorphic by using the linear systems. How can I tell if some graph can't be produced from the linear systems?
Yeah, okay. I mean, off the top of my head, I don't know if there's a good answer there.
Because how would we decide if there's a new construction? That's really
yeah. Okay. I mean, I guess I meant not in maybe such even a formal sense. I mean, obviously, it would be good if you could show that actually there's no linear system that corresponds to this thing. But I mean, I don't know a lot about constructions of these linear systems that have quantum solutions, but no classical solutions. Except for that, of course, there's a lot of group theory involved. There's a group theoretic characterization. But I don't know how sort of practically useful that is. There's this construction from Arkhipov using incidence matrices, and that's sort of the one that I know the best. And outside of that, I don't really know it that well. So I mean, there is quite a bit of flexibility in building these graphs in linear systems, but I would be surprised if every possible example of quantum isomorphic graphs can be constructed in that way.
What about this bonus question? Where would it be useful to have the convex hull of this tensor product? And why you cannot just take the tensor product of the just plain permutation matrices in it?
So, okay. So the reason I put it as a bonus question is because it's not really related very directly to the stuff that I talked about. It is related to quantum isomorphism, actually, though, because these convex hull of these P tensor P's, this essentially corresponds to the kind of classical correlations for the isomorphism game. And it just, of course, for the convex hull of the permutation matrices, like everyone knows, this is the double stochastic matrices. You get a very nice description. Maybe this is known. It seems like the type of thing that might be known, but I sort of have bumped up against it a few times in the past. And it would be I think it'd be interesting to understand what this convex hull looks like. Is there some nice kind of, I guess, like hyperplane description or something like this, right? We know what the vertices are, right? But sometimes it's nice to have like a sort of dual description, I guess, or whatever. It seems a natural question as well.
In your example, you use K33, the one of the first examples. So the other obvious choice is K5. Or have you what happens if you use K5?
You get a bigger. The issue is that already K33 you get 24 vertices, which is it's not huge. But if you're trying to like kind of, I guess, understand it, what's going on with the graph, then at K5 you get 40 vertices. You get, I think it's still a Cayley graph. I don't know what group it's a Cayley graph for.
So is the fact that K33 is bipartite, does it make it easier to kind of understand?
You can kind of see that there's this structure, of the graph that sort of looks like K33 in a certain sense.
Yeah.
I don't know if it being bipartite really matters a whole lot. The graph you get is not bipartite, but of course you could. You can also use this second construction I talked about, and then what you get. I'm gonna have to. It's harder to scroll on this iPad than with the arrow key. Arrow key. You can't get everything you want all the time. Okay, yeah. So, if you use this sort of second construction I talked about, you still get quantum isomorphic graphs. Essentially, you just get rid of these four cliques. You get rid of the edges and these four cliques everywhere, and also kind of the two graphs swap. So now the homogeneous one is this one, and the non-homogeneous one is this one. So you get essentially the same graphs, but you have fewer edges, so that's kind of nice. But you don't get this reformulation of the four color theorem. It just happens that, actually it was Crystal who was like, oh, you should put these graph 6 strings into like House of Graphs or something and figure out what these graphs are. I didn't even know you could do that. And so she's the reason that I even know that these are Cayley graphs for S4. And they turn out to be really cool, like nice ones, right? The edges going across here are the 4 cycles, and here are the transpositions. Well, not as they're drawn, actually, but anyways, up to isomorphism, that's the case. I don't know what happens. I don't, like I said, you still get some very nice graph for K5. But it's just so big, and I don't really understand sort of. It's some Cayley graph again, but I don't really understand sort of any more about it than that. I mean, it has integer eigenvalues. I think he has like 4 integer eigenvalues or something.
Thanks for a very nice talk.
Are these two graphs like are these the smallest examples that you have for?
These are the smallest known examples. I mean, I guess it's an interesting question whether they're the smallest possible examples.
Okay, so that's not known.
It's not known. So I think we know that you need at least, say, 16 vertices or something like this. But there's a gap, right? I mean, this is 24, so 24 is enough, but you need at least 16. I mean, I guess, I don't know. I wouldn't be so surprised if they're the smallest, but I also wouldn't be too surprised if there's some smaller ones. It'd be cool if there were some smaller ones.
Yeah, yeah.
There are, I should say that if you allow for sort of quantum graphs, then there are smaller ones. So the Peterson graph is quantum isomorphic, is some quantum graph, but I don't understand these quantum graphs so well. So that's kind of a different, has a different flavor in a lot of ways.
Okay. Yeah.
Maybe just a comment. S4 is also known as the octahedral group, which is also known as the qubit-Clifford group. Right, so you have basically Z2 cross Z2 semi-direct with SL2 over F2, and so maybe there's some interesting structure to be discovered there, or maybe there's some connection to quantum information, or maybe there's some new. Maybe we can actually solve this open problem of the 4-color theorem.
Yes. Well, so I did mention that there's this other construction by Musto-Verdon and Reuter using these subgroups of central types. So, I mean, if you're really thinking in terms of groups, then I mean, it's probably good to look at that. I never completely understood that construction. I know that you can get this pair by. I mean, you look at the automorphism groups of one of these graphs, and then you get like Z2 cross Z2 as a central type subgroup, which I don't remember what the definition is of that. And then you can use that to construct the other one in the pair.
Well, here the Z2 cross Z2 I'm describing is really more a quotient. Well, oh no, it is a subgroup because it splits. So I take that back. But it's not a central subgroup.
I mean, I didn't say it was central. I said it was well, okay. I don't know.
What does central type mean? Maybe I missed that.
No, yeah, I don't remember. So it's something I hadn't heard of before. I ran into their work. So it's something to do with 2 co-cycles.
Yeah. Very interesting though. Nice talk.
David, you were mentioning the quantum isomorphism implies co-spectral. So quantum isomorphism sort of sits between co-spectral and isomorphism. Do you have some idea of whether it's closer to one or the other?
I mean, what does it mean? I would say, okay,
given 2 not co-spectral graphs, what's the likelihood that they're quantum isomorphic? Or given 2 non-quantum isomorphic, what's the likelihood that they're isomorphic?
Sorry, I think you swapped the nons.
Oh, possibly.
Yeah. I mean, I don't know a real answer. I would say that probably like if you take a pair of co-spectral graphs randomly, whatever that means, then they're almost never going to be quantum isomorphic. If you take a pair of quantum isomorphic graphs randomly, I mean, yeah, I don't know. I would need to think, because maybe actually there's a way of coming up with a good answer there. But,
I mean, this list of results from counting homomorphisms with different class F sort of suggests some idea there. It's sort of like saying planar graphs sit between cycles and all graphs.
Yeah, I mean, I feel like it's closer to isomorphism than co-spectrality. I mean, there's a lot of stuff between co-spectrality even, well, I mean, you could at least say this like a chi-width at most 2 relation. And this is already, I think, quite a bit stronger than co-spectrality.
Yeah, another comment is it's co-spectral with co-spectral complements.
That's true, right? That's our, yeah.
Yeah,
already different from
that's a
co-spectral.
comment to Mike. I know you knew it.
Yeah.
Since I'm interrupting, I have a question. Some of those constructions you're using the end seem very similar to the construction that Kai Fura and Immerman used when they're working on the camp examples.
So that's actually, I probably should have mentioned, I mean, so the way we originally came up with this construction for these quantum isomorphic graphs is that we talked to Albert Atzerius, who's the author of the paper, and he explained these CFI graphs in terms of these like linear systems. And we sort of said, oh, this is looking like these kind of like these linear systems where you have these quantum solutions, but no classical solution. So maybe we can somehow use that. And then he went off in the afternoon and he figured out how to do it basically. Originally, the construction was slightly different because you also had vertices that correspond to just variables. But you could get rid of those and just have the ones that correspond to constraints.
There are a number of variants of the CFI construction.
Yeah.
It'll work this as well.
Mm-hmm. I can go back to these graphs that have the same number of homomorphisms from any max degree 3 graph. So I don't know how easy it is to tell from the picture, but I think this graph is just take a K5 on like this vertex, this vertex, this vertex, this vertex, and this vertex, and then you subdivide all the edges not incident to this vertex in the middle, and then you add an isolated vertex. So that's what this graph is. And then over here, this is actually just like a cube, and you've added a vertex of degree 1 to 4 vertices that form a tetrahedron. I mean, other than the construction I showed, I mean, like I wouldn't have known. I don't see how to see that like they had the same number of homomorphisms from graphs of degree -3. So yeah, I don't know, it's pretty weird.
Now for the first examples you gave from the K13, they're the ones that Brent and I used in that what we called local switching to construct co-spectral graphs.
Mm-hmm.
And the way you prove the co-spectral is you write down the change of basis matrix.
Mm-hmm.
You can actually write down the orthogonal matrix with any particular problems. It's not impossible. You can do something similar in this case.
Mm. Yeah. Another question I had I think on that last slide is, I mean, if I look at this relation you get by looking at graphs at counting homomorphisms from graphs at degree max degree at most 2, then this is just paths and cycles essentially. So you get co-spectral plus co-spectral complements. This is a nice description of this relation. Now, what about for graphs of max degree at most 3? Is there some nice algebraic description of this relation you can get? And then max degree 4, right? I mean, that would be really cool if there was. But I don't know.
It's a very nice question. It's not all clear to me what would happen.